In the previous class, we talked about the non-contiguous memory allocation, in which we have seen that if we doesn't have the place to put the uh, process into the main memory, so we divide the process into different pages, and that particular pages we put into the main memory. So what is paging? So paging is a main memory scheme that eliminates the need of contiguous allocation of physical memory. This scheme permits the physical address space of a process to be non-contiguous. So what happened here is, let's say if we have a process, and that process consists of, let's say, uh, the process is divided into four parts. Let's say P1, P2, sorry, P0, P1, P2, and P3. Let's say this is the process. So that process will be allocated into the main memory based on the pages that they have. Okay. So what we do here is we divide the process into number of pages, and the main memory is also divided into number of partition, that is called frames. The page size, let's say this is one page, so the page size and the frame size will be the same, so that these processes could be accommodated. Let's say there is process 0 will be accommodated here. Let's say the page 2 will be allocated for the process. Here, let's say page 1 will be allocated, and let's say here page 3 will be allocated, if these are the free spaces here. So this is the way how the non-contiguous allocation will be done into the physical memory or the main memory, right? Now this is called paging technique. So here the process is divided into number of pages, and the main memory is divided into number of frames. We map this particular pages into the frame. The page size and the frame size would be the same. Why it would be the same? The reason is, if the page size uh, is less than the frame size, so what will happen is there will be the problem of internal fragmentation. Means, let's say if the page size is, let's say, 1 KB, and let's say the frame size is, let's say, 2 KB. So what will happen is, so whenever we put the page into the frame, the 1 KB will be of internal fragmentation, and that we do not want. So generally, in the paging, what we have, if we assume, is the page size will be the equal to the frame size. So this is the page size, this is the one page size, and this is the one frame size. Both will be the same. Now let's talk about some more detail on here, right? Now let's assume that the CPU is generating, okay, we know that the CPU generates a logical address, okay? And this logical address belongs to the process, right? Belongs to the process. Now this logical address, they will generate in the form of bits, form of some bits. Let's say it is generating n bits. So the process size will be of 2 to the power of n words. Now here the logical address is having the bits, and the process will have the physical address space. This is the physical address space. Sorry, logical address space. This is the logical address space, and the size of the logical address is 2 to the power of n words. Okay, and we can convert this to the logical address also. So how many bits are required for that? So if the process is of 2 to the power of n words, it means that n bits would be used to represent the process and the word here in the process. Now, whatever logical address the CPU will be generated is for the process, right? Now, but the CPU will get the get the bits, get the bytes or the word from the main memory. That we all know, right? So main memory works on physical address, and the physical address is also in some sort of bits. So let's say assume that there are m bits to represent the physical address. So the physical address space will be 2 to the power of n words for physical address. So the total physical address will be 2 to the power of n words, that is called physical address space. So the logical address, which is generated by the CPU in terms of bits, the physical address space that we can see, physical address is the bits for representing the address into the main memory, and the physical address space is nothing but what is there in the main memory. Logical address space is nothing but what is there in the process. So what is logical address space or virtual address? This is also called virtual address. Okay. So logical address or virtual address represents in bit address generated by CPU. CPU for what? For process. Logical address space or virtual address space represents in word or bytes the set of all logical address generated by the program. So the program or the process generates the address which is called logical address space. The CPU generates the address which is called logical address. Physical address. What is physical address? Represented in terms of bits. An address actually available in the memory unit. So here we have the memory unit in which whatever address we see in the form of physical address. Now what is physical address space? It represents in the word of the byte the set of all physical address corresponding to the logical address. So corresponding to the logical address, whatever the physical address space we have, that is the physical address space we are getting, right? So here what will happen is the CPU is generating the CPU is generating the logical address or virtual address that will be converted into the physical address using a hardware or software or the combination of that unit is called memory management unit, which will make a translation from logical address to physical address to get that particular word or the instruction that is required by the CPU and will be fetched. This is how the address mapping will be done. Now let's talk about the logical address. Let's say the logical address generated by the CPU is 31 bit. Then the logical address space will be 2 to the power of 31 words. Okay. It means that we have 2G, 2 gigabyte of words or 2 gigabyte of words. So it will be 2 to the power of 30, right? Logical address space, let's say logical address space is 128 MB, then MB words, then it will be like 2 to the power of 7 for 128, and MB will be 2 to the power of 20 words. Then the logical address will be log 2 to 2 to the power of 27, means 27 bits. So from logical address, we can convert to logical address space. From logical address space, we can convert to logical address bits, how much it is required. Now, what is physical address? Let's say the physical address is 22 bits. So physical address space will be 2 to the power of 22 words. It means 2 M words. If the physical address space is 16 M words or 16 mega words, then it will be represented as 2 to the power of 4, which is of 16, and 2 to the power of 20, which is of mega words. Then physical address is required as log 2 to the power of 24. It will be 24 bits. We can represent it. Okay. So the mapping from virtual to physical address is done by memory management unit, which is a hardware device, and its mapping is known as the paging technique. So whatever is mapped is called mapping technique. The physical address space is conceptually divided into number of fixed size block that is called frame. The logical address space is also split into fixed size block, which is called pages. Here we have to remember that page size will always be equal to the frame size. Okay. Now let's take one example. Let's assume that we have the process, okay, and the total process size of the process is, let's say, 4 byte. Okay. Now the second thing is, now what is the size of the page? Let's say the page size. Page size. I am assuming the page size is 2 byte. How many byte? 2 byte. Now for that, the number of pages required will be 4 byte into 2 byte. It will be 2, number of 2. So 2 pages are required. So I am putting here 2 pages. So the total process will be divided into page number 0 and page number 1. Right? This is my page. Now inside the page, one page size is of 2 byte. I am assuming that 1 byte means one word is nothing but 1 byte. So here the process, because the system is byte addressable, or we can represent this as a word. So the whole process will be divided into 2 pages, and in each page we have 2 bytes or 2 words, which will be represented as, let's say, word number 0, word number 1, word number 2, and word number 3. Getting it? This is how page will be, and inside that, this is how the process will be stored. So this is my process. Now I want to put this particular page into the main memory. Where? Into the main. Okay. So let's say, and let's say the main memory size. Main memory size. What is the main memory size? Main memory size is, let's say, 16 byte. Now here you see, what is this? This is a logical address space. What is it? Logical address space is of 4 byte. Here, the physical address space is of how much byte? 16 byte. Okay. Now, what will be the frame size? Frame size. Frame size will be the same as the page size. So it will be 2 byte. So how much frame will be there in the physical memory? The frame will be, number of frame will be 16 by 2, it is 8. So 8 number of frames will be there. So let's say the whole main memory is divided into, so this is 0, 1, 2, 3, 4, 5, 6, and one more part will be 7. So this is my main memory, which is you can take it as a physical memory. Okay. Now I'm putting this particular pages here. So in the frame also, because it is of 2 byte, means 2 words. So each frame will have 2 words, right? So let's say here we have so I'm putting into, let's say, another color. It will be, so it will be, let's say, 0th word and first word, second and third word, fourth and fifth word, sixth and seventh word, eighth and ninth word, 10th and 11th word, 12th and 13th word, and 14 and, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and this is 15. So as you can see, how many are there total? 16. So 16 words are there. Getting it? Now assume that this block are occupied. Okay, so what are the free frames here? Free frames are frame number 1, frame number 3, frame number 4, and frame number 7. 1, 2, 3, 4. 4 frames are occupied, from 4 frames are free. Now, here, let's assume that we are doing the mapping of the frame with the pages. And let's say here in this particular place, we have occupied page number 0. And let's say here we have occupied page number 1. So when we occupy page number 1 here and page number 0 here, so what are the free frames right now? So the free frames will be frame number 3, which are free, and frame number 7 that are free. So which two frames are free right now? Sorry, frame number 7 are free, 4 are occupied, right? So 4 is occupied. So 3 and 7 are free. Okay. Now, we doesn't have to do much here, but we have to thought out like process P0 is allocated in frame number 1 and process P1 is allocated in frame number 4. Remember, I talked about the memory management unit, which is converting the logical address into the physical address. Here, in this particular example, that will be the page table. There is a page table concept into the paging. So the page table is nothing but a table which is for each and every process. So for this process, let's assume that this is process 1. So for process 1, we have the page table. So this is the page table for that. In this, we have the frame number. So frame number 1 is allocated here, and frame number 4 is allocated here for page number 0 and for page number 1. Getting it? So for page number 0, frame number 1 is allocated, and for page number 1, frame number 4 is allocated. Get it? Now the CPU is generating one address. Assume that the CPU is generating an address. That address is called logical address. Let's say it has generated 2. What it is generated? 2. Now it is generating 2. 2 means it required this particular word from the process. This particular word from the process, which is required by the CPU. Okay. Now, where it is right now? Where is the place for this particular 2? The place is here, as you can see. Here you can get from page number 1, the first word you can get here, because it is requiring 2 means this particular word it is requiring. Okay. Now what we do is, as we know that it is generating the bits, right? So what it is generating? 2. Now the logical address is in the form of, it will be like this. The logical address is in the form of like this. We have two part of logical address. One part is called page number. Another part is called page offset. Both will be represented in the form of bits. Now, how this decimal number 2 will be converted into binary? So this is the decimal number. We need to convert into binary. So it will be look like this. This will be 0, 0. This will be 0, 1, and this will be 1 and 0. Now let's come here. Now this is the logical address space. How will convert the logical address space into the physical address in terms of bit? So here you know that it is of 4 bits. It means that if we'll convert it into log base 2 4, it will give me 2, means 2 bits. To represent this particular logical address space, I required 2 bits. How many bits? 2 bits, and that will be 0 or 1. That will be 0 or 1. So for that I required, for that I required how much? So it will be 2 to the power of 2. It will require 2 bits. So I required how much of 2 bits for this representation. That's why it is having 2 bits. Now, what is the page size here? What is the page size? Page size is 2. To allocate 2 pages, how much bits are required? We require 2 bits. So page size is nothing but my offset. So it required 2 bits, 0 and 1. So with the help of that, we can use it. So 1 bit is sufficient to represent 2, means 0 and 1. 0 is of 1 bit, 1 is of 1 bit. So for page number, 1 bit is required, and for page offset, 1 bit is required. In case of here, this will be for the page number and this will be for the offset. So this is the page number and this is the offset. Getting it? Now, the logical address says that the page number it required by the CPU is first page number. Now, where is the first page number? First page number, you can find it in frame number 4. Now, frame number 4, where will represent the frame here. So representing the frame denotes the physical address. To represent the physical address, here also we have 2 parts. One is the frame number, and the second is the frame offset. Now, what is the frame number that we are getting? Frame number is 4. So for representing number 4, how we can convert into the binary? For that, if you see here, how many bits are required to represent the physical address? So you see, you have the physical address space is 16. So to convert the physical address, you need to do log of base n of 16. So how much you will get? 2 to the power of 4 means you will get 4. So the length of this will be of 4 bits. Now for the offset, we know that how much we require, because the offset is means how much is the frame size. Frame size is of 2 words. So for 2 words, we required 0 or 1. That will be the same as that. So here required. So here it will be the frame, as we know that this offset will be the same as here. So we'll put here. And the frame is 4. So how we represent 4 into the binary? So it will be how much? It will be 2 to the power of 2. So it will be 1, 0, and 0. So it will be represented as 4, and this will be represented as this 0. And you got 4 bits. So 1, 2, 3, 4. So 3 bit is for the frame number and 1 bit is for the offset. Why 3 bit for the frame number? Because what is the frame number? Frame number is from 0 to 7. So how you will denote 7? 7 will be 1, 1, 1. 6 will be 1, 1, 0. 5 will be 1, 0, 1. 4 will be 1, 0, 0. 3 will be 0, 1, 1. 2 will be 0, 1, 0. 1 will be 0, 0, 1. And 0 will be 0, 0, 0. In that way, we represent in terms of 3 bits. So here we required 3 bits, we have done, and here we require that. So how we'll convert to 8? So you can see the representation of 1000 will be of 8 here, will be of 8 here. But what we required frame number 4. So the frame number 4 here we are getting, and we required which one? 0th word. So this is the 0th word. So the 8 will be fetched here, and this 8 will be given to the CPU. So this is how the translation will be done from physical address, so from logical address to physical address. Now, if we take this, so the CPU generates the logical address. Logical address is of two part. One is the page. This is the page number, and another is the page offset. This is the page offset, and the page, from the page will get the frame, and frame will see in the frame ID, and the offset will be the same as the offset, and whatever the value is, we are getting the frame we are getting first, and then we'll locate for the offset. This is how it will be done. So first we'll get the frame, and then we'll see what is the offset here.